Good morning. Welcome everyone to day 2 of our HWO conference. My name is Michael Bottom. I'm from the University of Hawaii, and I'm joined by our virtual moderator, Jessie Christiansen from Caltech. Today we have a great set of speakers, and just a few reminders. Please don't congregate in the steps or in the back. That's a fire hazard. We'll have the speakers give their talk. The first one will be 15 minutes, and then we'll have 5 minutes for questions. And afterwards, so our first speaker is Professor David Singh from Johns Hopkins.
All right, hello, can you hear me? All right, so thank you very much for having me today and making it to this morning's session. So HWO is aiming for a 25 planet survey of Earth-like planets. But what does a planet survey look like when you actually have 25 real planetary spectra in hand? Well, we've been doing the first planet surveys with HWO's predecessor, Hubble, and now more recently, JWST. So what are the lessons learned we can take from this exercise? And when we have 25 spectra from nature, what can we learn going forward? And how does our view change when we have new powerful facilities come online? So let's get into it. So I'll talk today about transiting planets. We heard a little bit yesterday about transiting planets. So a quick introduction for those who are unfamiliar. A transiting planet is one that passes through its star as viewed from the Earth. And these are incredibly information-rich events. For one, you can measure the planetary radius, a fundamental parameter, and you can measure that very accurately and very precisely. So the planets that transit tend to be close in, so we're talking about the warm to hot planets, and you can also measure the planetary spectra from these events as well. And here's the landscape of sort of what you can access with transit spectroscopy with JWST today. So here we have a plot of planetary mass versus orbital period, and I've shaded in the region you can do transit spectroscopy. JWST has looked out to transiting planets at 1,000 days orbital period and down to Earth mass planets. So it's a wide range of planets we can look at. So how do we get the spectra from these planets? Well, during the transit event, some of the light will filter through the atmosphere and leave its spectral imprint. And at those wavelengths that are spectrally active, you can measure an increase in the radius of the planet and measure the transmission spectra. So what you end up doing is measure the radius as a function of wavelength and build up a transmission spectra. And you could also think of this as an absorption spectra. And it's a very special part that you measure the spectra as the planetary limb, this day-night boundary of the planet. Now, when you have a facility like JWST, you could actually push this even farther because you have enough signal to noise to even measure the transit spectra during ingress and egress. And actually, you can slice the planet in half and only measure one side of the planet, the spectra, and then you measure the other side too. So I like to call this sunrise sunset spectroscopy, and now we can get transmission spectra for different sides of the planet and start to get 3D information about the planet. And this is something that's only been possible with JWST. So let me start with Hubble. Hubble has a very rich history of doing exoplanet atmospheres. I don't have time to get into it all, but it launched the exoplanet atmosphere field, many fundamental discoveries such as the first atmospheric detection, the first atmospheric escape in the far ultraviolet, and our first look at different planetary types, giant planets, Neptunes, sub-Neptunes, and even starting to try to do terrestrial planets. What I'll focus on is planet surveys. So Hubble started to do the first planetary surveys, and these are the hot Jupiters. These are the first planets you can actually study the entire population and get spectra for and look at their atmospheres. So here's the first 10 hot Jupiters Hubble did. And for all of these, you can see sodium and potassium and water feature there, 1.4 microns in the near infrared. And you can see there's a couple of takeaways from when you now look at these spectra. For one, the features are all smaller than we predicted. Like the 1.4 micron water feature is about a third the size that people had predicted going in. And it's because clouds and hazes are covering a lot of the features. So you can see those clouds and hazes in the optical as these slopes, these scattering slopes. And the other kind of key takeaway is from these first 10 planets, no two planets really look the same. And this is kind of surprising because these are Jupiter, hot Jupiters. They're should be kind of more simple as far as like we know the bulk composition is hydrogen and helium. Yet none of these two planets are the same. There's a large diversity in the planets. All right, so let's kind of fast forward to more recently. Let's actually look at the whole 25 planet comparative study. So this is from the HST PanSet survey. And now here we have a full rich set of 25 planets. These are all hot Jupiters. And one thing when you do comparative planetology, you want to try to correlate a lot of the spectral features with known parameters such as equilibrium temperature or planet mass or radius. And you don't have to look at the corner plot too much in detail, but the bottom line is there's no strong correlations trying to predict any of these features. So even with the hot Jupiters today, we cannot predict exactly, oh, this one, because it's this temperature and mass, it will have this size of water feature, it will have this sort of cloud and haze property. So the takeaway is the planet population, even for these giant planets, is very diverse, and clouds are meeting a lot of these features. So kind of lesson learned, we probably need hundreds of planets at higher signal to noise to really uncover these subtle correlations. Well, that's higher signal noise is right what we're getting with JWST. And I mean, JWST is absolutely amazing for planetary work, especially transiting planets. We've learned more in the last 2 years than we had in the previous 25. And here's just it's well worth the wait. This is why you do flagship missions like this. So few notable results. There's the first exoplanet detection of CO2. And this was like right out of the box when we started getting data. The first exoplanet detection of photochemistry, and that's a SO2. There's a little feature down there of SO2 you can see. I mean, photochemistry is a key process you're going to want to know as you go down to terrestrial planets. And our first in-depth look at smaller sub-Neptunes. So JWST is also doing planet surveys, terrestrial planets, trying to look for atmospheres on those, and then sub-Neptunes, which are a new exciting field. But I'll focus on the giant planets and the Grand Tour program, which again is a 25 planet survey of giant planets, Neptunes up to Saturns to Jupiters. So let me just show you the first stop on the Grand Tour. This is WASP 94AB. This is a rather typical hot Jupiter, 1600 Kelvin, about half a Jupiter mass. And there you can see on the left is the beautiful transit light curve you get from JWST. I mean, the signal to noise is absolutely phenomenal. And when you take the spectrum, you see on the right there, you see 5 water bands at high signal to noise and a cloud covering up all of these features. And this is kind of what you expect based on all of those previous results from Hubble. Strong water features, but muted by clouds and hazes to be smaller than you might otherwise predict. So that's expected, but there's something surprising. One, if you take this spectra and do models, retrieval models, you find it's very metal rich, something like 100 times enhanced and heavy elements, rather than something more like 5 to 10 times enhanced, what you expect based on the solar system. So that's very surprising. That would be very surprising from planet formation to actually have a planet this enhanced and this heavy. Also, it's very carbon poor. There's not too many carbon species that's really visible in the spectrum, and that's also rather surprising. But there's a large caveat here. When we did the analysis right here, This is the classical spherical analysis. You pretend the whole planet is just one homogeneous sphere, and the planetary limb is just a homogeneous annulus. This is what we've been doing for a long time with Hubble. But of course, with JWST, we can go further and we can do a limb-limb analysis and actually fit the light curves, measuring both planetary radii from the morning and the evening. And when we do this, we take the same data and do a limb-limb analysis. What we find is a very strong limb asymmetry on this planet. So here in red, you see the transmission spectrum from the evening side of the planet. And now you see very large water features. Remember, this is the same data as I just showed. Very strong water features, and the cloud is confined to millibar or lower. And on the morning side, you see a very high altitude cloud covering all of the features. So instead of the clouds muting the features, they've actually been separated, and they actually separate quite well. Just pretty clear transmission spectra in the evening and a cloudy in the morning. And this dilutes the features and actually leads to a huge bias when you analyze this thing spherically. So instead of 100 times solar, if you take that red spectra and you model it, you get something more like 3 times enhanced in heavy elements like you expect. And all the other properties like temperature, C/O ratio are biased as well. So the features are bigger here when you do this spherical analysis, but the noise is a lot larger. So you really do need big telescopes like Habitable worlds. So you might ask, like, oh, that's one planet. Does that kind of hold for the other planets too? And it looks like it is. So here's some recent results. Here's a 9-planet, first 9 planets for JWST. We're looking at limb asymmetry. And you can see for all of these planets, the morning spectra in blue and the evening spectra in red. And throughout, it's a pretty common trend that you find predominantly the evening spectra the evening limb is the one that's pretty clear, and the morning is very cloudy and has high altitude clouds. And we think this is likely tied to the day-night cloud cycling, where on the day side, it's hot, the clouds evaporate, they go over the evening where it's clear, and then on the night side, they condense, they're lofted to high altitudes, and basically cover the entire morning terminator in clouds. So all of these previous results that, from Hubble and so forth, those interpretations could be very biased. And we didn't really see that until we had this new powerful facility. So what are some of the lessons learned from this exercise? Well, one of the first ones for me is the atmospheric signals are usually smaller than predicted. And clouds is usually the culprit here. And the other is, with such a large diversity in the planets, when you see one planet to the other, 25 planets isn't really quite enough to actually do the proper comparative statistics as you need. So you need more planets. And then the third one is decades-old assumptions could be wrong. And in this case, the limb asymmetry for hot Jupiters is a first-order effect you have to worry about. And if you don't, there's a potential for a large bias in interpretation. So what can we learn from the Hubble going to HWO? I kind of think it's worth noting, here's the 25 planets from Hubble, and the spectral range and wavelength and signal to noise is going to look very similar as the ones you'll get out from Hubble World Observatory. So you can see on the right there's from the simulator various Earth-type planets with like an 8-meter, 10 parsecs, and so forth. So this is kind of what these planets are going to look like. Same wavelength range and everything. But instead of worrying if one of those little bumps is potassium, you're going to be worried if it's actually a biomarker signature. So I think the lessons learned from Hubble here are pretty relevant. So for for Habitable Worlds, what does this mean? Well, exoplanet atmospheric signals are usually smaller than predicted. I would bet big money that will continue. You should use conservative signal estimates in the design phase. And the large populations are needed. So 25 planets, this is a great first start. It's definitely worth doing. It's really exciting. But you should really aim for a very capable telescope and really push yields as high as you can. And you're going to need large numbers for trends. And decades-old assumptions could be wrong. So you want to have a diverse set of models and tools needed to challenge conventional thinking, think about things like viewing angle and clouds and spatial homogeneities and so forth. So I'll just, one last point here. With HWO, if you're able to do transits really well and direct imaging really well, you'll see the whole phase space will be covered, and you can basically study the entire galactic exoplanet population with a facility like this, and that's really exciting. And with the transits, you can do comparative studies on the warm to hot side, study photochemistry, look at the inner edge of the habitable zone, and this is how you're really going to put these Earth-like planets in context, is be able to see all the planets, and HWO will be able to do that if you can do it with transits and direct imaging. So with that, I'll leave my conclusions.
Okay, do we have any questions from the room? Yes, in the blue shirt.
Hi, thank you. So I was curious about this asymmetry, limb asymmetry, and you mentioned morning and evening sight, but aren't these planets tidally locked? So I wasn't sure what morning and evening means here. And that leads me to ask, what's the physical reason for this asymmetry? What's causing it, right, in the cloud coverage?
Yeah, so these planets are tidally locked because they're really close in. And so you have a permanent day side and a permanent night side. And so the atmospheric circulation will naturally push all the atmosphere to one side, and then that will be the evening. And all of the hot atmosphere will be moving over that evening side of the terminator, and then it will move down over to the night side where it will cool off. And that's where clouds condense. Because it's cooler, you're moving on the other side of the condensation curves. So in this case, for hot Jupiters, it's things like magnesium silicate clouds are really thought to be the dominant process, and that really looks like what we see here for this planet. And then that cooler material moves over to the other side, the other limb, and it's cooled off, and then that makes those high altitude clouds. So that then gives the asymmetry.
Hi, I'm Edwin from RIT. So I was curious about the also limb-limb asymmetry. I was wondering if there's enough signal to also further divide that by latitude, if that would show any differences.
Well, we're hoping so, but it's tough. So you can imagine, instead of just fitting 2 planetary radii, why don't we fit 3? But all of a sudden, it becomes a very degenerate problem. We have 3 planetary radii. People are looking into this now, what sort of signal to noise you need to actually be able to see that sort of difference. So far for these planets we've tried, and we can't really get more than, it seems like just 2 separate limbs is pretty good to JWST and first order. And so probably need quite a bit higher signal to noise to actually pull out like a pole spectra.
Any questions from online?
There is a question, yes, from Michael Best. As we push towards the next generation of atmospheric retrieval, do you see any advantage in shifting away from fixed field optics towards modular multi-instrument arrays in space to better address degeneracies in transmission spectra? Modular multi-instrument arrays.
Multi-modular instrument arrays, which I'm not too familiar with those instruments. But I will say, basically, whenever we've done these sort of surveys, wider wavelength coverage is really key. So the wider coverage you have with whatever instrument you're using is very important.
Maybe I'll add on to that. We've talked a lot about designing HWO for the direct imaging. Are there any design choices we should make for transmission spectra and transits?
Yeah, so as you're thinking about your spectrograph on HWO, I think you can learn a lot of lessons from JWST. So for instance, on the near spec instrument, midway through the mission, they punched a big hole in the middle of the near spec instrument, 1.6 by 1.6 arcsecond slit, and you can put your star there and not worry about basically any sort of slit losses or light losses, because those are really detrimental to transit work. and it works beautifully. And I would say the data is a lot cleaner than, say, the slitless sort of spectrographs. So, when you're already designing it to be so stable, that's basically one of the, key things JWST unlocked for transit planets, just like such a stable instrument. So you already have that for free. And then if you just worry about light losses and things like, you're looking at bright stars, you're not just trying to dim it out. You need to be able to read that without saturating. Those sort of design choices will be key to think about.
Okay, let's thank David again. And our next speaker is J.B. Ruffio from UC San Diego.
Mic check, yeah. Okay, hi everyone. So my name is Jean-Baptiste. I also go by JB, like Mike said, I'm a research scientist at UC San Diego. So what I'll talk about today is to discuss the potential of moderate to high resolution spectroscopy for detecting biosignatures and so for HW. So this is a slide you've seen before. So this is a notional instrument suite for HW. And so what I want to focus on is this high contrast spectroscopy mode. And so far, we've often been assuming that we would use a low resolution spectrograph, so a resolution of 140. And I mean, I'll be direct. So basically, my goal today is to convince you that we should seriously be considering probably a moderate or maybe a high resolution spectrograph, so a resolution of 1,000 and above, probably. So this is a model of an Earth analog, assuming high clouds from Renew, and I can zoom in on the oxygen feature right there. So we just backtracking a little bit, we define spectral resolution as the wavelengths divided by the width of the line. So the higher the spectral resolution, the finer the spectral features we can see. And if you're at a resolution of 140, the width of the line is basically the entire width of that zoomed in region. If you go to higher spectral resolution, like 1,000 or 10,000, then you can start to resolve the very fine spectral features, like the barcode of molecular species. And that has several advantages. First, there's just more information, so there's more signal. But also, it allows you to reject more of the background light. So let's say the exozodi or the residual starlight, because the light in between spectral features doesn't matter effectively. Of course, when we go to high spectral resolution, we also spread the light over more detector pixels. So detector noise is going to be more important. So there's going to be a trade-off. And talking about trade-off, there has been basically two types of trade studies so far. There have been some at low spectral resolution, up to a resolution of a few hundred. One of the caveats here is that we have not yet included correlated noise, so residual speckle noise in those retrieval. And I'll get back to it in a minute. Then there has been some studies at higher spectral resolution, so 1,000 and above. And here they've been typically relied on cross-correlation function and high-pass filtering. And I think here one of the main caveat is we probably don't need to high-pass filter the data, which means removing the continuum at a resolution of a few thousand with an ultra-stable spectrograph like HW. So all in all, there's really currently no comprehensive study of spectral resolution that allows apple-to-apple comparison between the low spectral resolution range, like a few hundred, to the high spectral resolutions, 10,000 and above. And I think that's really needed in order to determine what maybe the optimal resolution might be for the spectrograph. So getting back to the problem of the correlated noise, so this is a spectrum for 15189 so this is an integral fixed spectrograph, so we're scanning through the different wavelengths. The star is hidden behind the mask, has been subtracted, and you can see the residual speckles, so the residual starlight in the background, like that bubbling thing. That's correlated noise, and when we extract the spectrum of the planet, it's going to add like wavy things, wiggles into your spectra, and that has been an issue. So this is different spectra extracted from different observation and instrument for that planet. So this is a 2 Jupiter mass planet-ish. And the spectra don't always look very consistent. So correlated noise, speckle noise has been one of the major challenges for direct imaging over the past decade. We're getting better at it. And I think one of the ways we've been getting better at measuring abundances is actually by going to higher spectral resolution when we can. Another way to illustrate the problem with correlated noise is that if you're trying to detect a line, like at a low spectral resolution, and you have correlated noise in orange, and the scale, the length scale and the amplitude are similar, then you're not going to be able to detect the line, because there's no way to tell the signal from the noise apart. But if you go to high spectral resolution, then if you have the same correlated noise, there's no way for the noise to explain sort of sharp feature in your data. So you're going to be able to detect your, say, oxygen at high spectral resolution, I mean, unless there's too much noise elsewhere, but even in the presence of correlated noise. And so I just want to refer to a talk by Nicole Wolf on Thursday, who's going to dive a lot deeper into the problem of correlated noise, but I'll move on from here. So what we need to do first is define a signal-to-noise ratio, really, that accounts for all those caveats that I mentioned previously. And I think a nice framework to do this is like template matching, or call it match filtering, or maximum likelihood, all the same things in this context. The idea, if you have a planet model, call it M, and you have a model of your noise that includes also correlation, so that covariance. So if you have covariance in your planet model, then from those two things, you can define a signal-to-noise ratio for the planet that is valid at any spectral resolution, that includes a model of the noise covariance, and that also includes the shape of the spectrum that you're looking for. So I think that's a pretty nice framework. And you can also modify it to estimate signal-to-noise ratio for specific molecules. And you can do that, I think, pretty easily by just subtracting the envelope of your spectrum. And now what you're doing is measuring how much your spectrum deviates from a flat line. And that's, I think, what detecting a molecule is just detecting how much it deviates from a flat line. So sort of, sorry for the couple slides of like technical detail, but sort of equipped with that statistical framework, we have been simulating Exo-Earth observations around 164 stars using like a modified ExoSim framework. And this is just a very initial analysis. This is not, so we'll have to do more in the future, but we added like one planet. We assume we had one planet per star, but we spent 400 hours per star. That we were looking at 20% bandpass centered at 750 nanometers, so that we will look at oxygen here. We included a model of the covariance. We don't really know what the correlated noise is going to look like for HWO, as far as I know right now, but I'm just assuming a correlation length of like 10 nanometers, and we're going to vary the amplitude later. For the detector, it's not really a Roman analog, actually. This is a little much better than that, but this is sort of the optimistic range of the current technology as far as I understand it. But we're going to vary that as well in the next slides. So if I assume that the chronograph can reach a starlight suppression level of 10 to the minus 10, then we can start plotting things like this. So on the x-axis, I'm showing the spectral resolution. Y-axis is the signal-to-noise ratio. And every distribution here, vertical, like violin plot, is the distribution of SNR for the 164 star in my sample. So here I'm showing the signal-to-noise ratio per spectral bin, or per resolution element. It's not going to change very much. And as you would expect, the bins get smaller at high spectral resolution. Your SNR decreases. But at higher spectral resolution, you also get more bins. So if you combine the entire spectral range, your SNR really doesn't decrease, though your planet detection SNR doesn't decrease until the detector noise starts to dominate. And with the assumptions I was mentioning, that only happens at about a resolution of 1,000 in here. Having that ask an interesting question is that, could we just use a spectrograph maybe to detect planets? Is that a possibility? Because there would be a lot of advantages to using the spectrograph. We'd get a lot more information about the system. We could already do a lot of science right away. Now, if we look at the SNR, the signal-to-noise ratio of the oxygen feature specifically, then spectral resolution has a higher impact. The detection improves with spectral resolution first, again, until the detector noise starts to dominate, and then it decreases again. And that already gives us an idea of maybe what an optimal spectral resolution might look like. Obviously, that depends on all the other parameters. So now we can vary maybe the amount of correlated noise. So in the previous slide, I assumed very little correlated noise. I put the floor at 10 to the minus 13, but here we can change it from 10 to the minus 13 to maybe 10 to the minus 11, with the starlight suppression still being at 10 to the minus 10. You can see that the more correlated noise, the the lower the detection strengths overall, but the impact is stronger at low spectral resolution. That's because if the spectral resolution of the spectrograph is lower than you call it a noise, then it kills any signal, and you're not going to be able to recover that. We can also vary the amount of detected noise. So the middle row here is just assuming an undersampled spectrum instead of being Nyquist sample. So that shifts the optimal spectral resolution towards higher spectral resolution. And then for fun, also just assuming we might get completely zero noise detectors, what happens in the bounding case where we have no detector noise? And in that case, well, we just should pick the highest spectral resolution we can, because there's always going to be more information there. So this is just to summarize the idea beyond like determining the optimal spectral resolution. And I think the two main parameters are going to be detector noise on the right that sets the maximum spectral resolution, and correlated noise on the left that sets the minimum spectral resolution. And I don't know what those are, so I don't know what the optimal resolution is. But I think that highlights how important determining those is in order to be able to converge on the spectrograph. There's always going to be a lot more. I think there's going to be a lot of advantages to going to high spectral resolution. It's more robust. It tends to be more robust to false positives, I think, especially speckles with the correlated noise. From template matching, like a galaxy is not going to look like a planet at high spectral resolution. So it allows a certain level of vetting. I think we might there's a chance we could get more robust biosignatures, because at a resolution of like 10,000, it's really hard to create like that very specific signature of oxygen. And we should probably think about the broader range of planets and also science cases beyond just the Exo-Earth. So larger, quote unquote, easier ice and gas giants, for example. So I'll refer you to, so Beck Dacus, who's a student at UCSD, is working on that right now, a paper in prep. So he's somewhere in the building or in the room, maybe. Just go talk to him. And I'll do a call. I think we might not have, there's probably a lot of science cases that would benefit from a higher spectral resolution. So if you have any science case that would benefit from that, I'd love to chat. Just let me know. Like solar system science, galactic science, just yeah, let me know. So in this last part of the talk, I want to go back to the lessons learned, and maybe I should have started here, maybe. But the lessons learned from self-luminous planet, and especially JWST in the past few years. So moderate resolution spectroscopy, I believe, has enabled in the past several years the first population-level studies of directly imaged planet composition. So we have learned that massive giant planets that are far away from the star tend to have a stellar carbon-to-oxygen ratio. So maybe the carbon-to-oxygen ratio is not the best tracer of planet formation, unfortunately. We have also checked that larger objects, so 10 to 30 Jupiter masses, like brown dwarf regime-ish, tend to have a stellar composition as well, which would be consistent with a star-like formation pathway. But really the message here, what I want to say is that high-resolution spectroscopy from the ground is fairly routine. It's a mature technique. We know how to do. We know how to do atmospheric retrievals. We know how to detect planets, reduce data at high spectral resolution. So we have been more recently applying this technique to JWST. So JWST has a moderate resolution spectroscopy mode in NERSPEC and in MIRI, but I'm going to focus on NERSPEC here. So resolution of 2700. So we've been adapting the data reduction technique to this instrument, and this is the kind of results we're getting for HRH99, which is a multi-planet system. So 4 planets, 5 to 7 Jupiter masses, orbiting the star. Happens that the 4th planet is outside of the field of view here for reasons I'm not going to get into. We're still learning how to work with JWST. But the thing I want to highlight here is that NERSPEC was not designed for high contrast. There's no coronagraph. And yet it has proven to be one of the most powerful high contrast instruments on JWST. So here is the kind of spectrum we're getting from NERSPEC, and that I think illustrate the power of higher spectral resolution. Again, this is 2700 of resolution. This is HRH9c, the 3rd planet in the system, from 3 to 5 micron. So in orange, you have the data. sorry, in black you have the data, in orange you have the model. It's hard to tell them apart. So you see water and carbon monoxide across the entire range, but then the high spectral resolution really allows you to see the finer spectral features in specific species. So you have methane that's pretty clear up there, but you have carbon dioxide also around 4.3 microns, which is great to measure metallicity. We even have isotopologues at that resolution, so we don't even need to go to like several tens of thousands here. We can see them at moderate spectral resolution. But really what we have been excited about in this spectrum is the detection of sulfur on the top right here, H2S. And that's because sulfur is considered to be a refractory species. So what that means is that in the protoplanetary disk, where planets form, sulfur is expected to be only found in solid phase. And so by detecting the sulfur, we can trace solid accretion as opposed to all the gas around it, the gas giant. But we could retrace the solid accretion. And what we're finding is that so on the right panel, you have the carbon, oxygen, and sulfur enrichment in this planet. And they're similar to the ones in the solar system with Jupiter and Saturn. And I think that's very interesting and very exciting because that probably suggests that they probably form the same way. But HRS 99 is a system that's far more massive, like 5 to 7 Jupiter masses per planet, way more extended. And so that probably suggests that planet formation, like core and pebble accretion, extends to systems that are much bigger than we originally anticipated. So I'm going to end here on the takeaways. So first bullet point, I think a moderate resolution spectrograph could not only be more optimal, but actually might be necessary, depending on the correlated noise. So we really need to own in on what we expect the speckles to look like for HWO. I believe there's always going to be more science opportunities if we go to higher spectral resolution because we can see more things. There's molecules that are only detectable at high spectral resolution. For example, the sulfur in the HRH9 planets with JWST. We would not have done that with a low resolution spectrograph. And so to finish, yeah, I think moderate resolution spectroscopy with JWST is proving transformative. I only touched a little bit on everything that we are working on. And I think it might prove transformative for HW as well, but still need to figure it out. Thank you.
Questions from the room?
Hi, JB. Great talk. John Debus, Space Telescope Science Institute. Hey. So in this trade study that you've done, did you play around with any other parameters such as like backgrounds from ExoZodi or anything like that? Would that cause any issues?
There is ExoZodi included, but we have not been varying it. There's a lot more work to be done exploring the parameter space, absolutely.
Dave Charbonneau, Harvard. So in the trade study, did you typically when you build a higher and higher resolution spectrograph, the throughput goes down, and you even get to the point where you have to, the architecture fundamentally changes. At even higher resolutions, you might have to cross-disperse just to deal with the detector.
We didn't include that, yes.
Okay, so you didn't consider any losses in throughput, for example?
Yeah, there's a throughput term, optical throughput term here. It's just constant as a function of spectral resolution.
Okay, so the only penalty you considered was
detector
the
noise.
detector noise.
Effectively, yeah.
Okay, great, thank you.
Any other, Tyler?
That was really, sorry, that was really interesting. I was curious if you had considered in this any trades against bandpass between the resolutions.
Again, we'd love to. This is as far as we've gone so far. But yeah, we should do that.
Yeah, and in terms of the correlated speckle noise, have you looked at anything like HCIT data or anything like that? Because
not yet. We've started talking about it.
Yeah, that would be really interesting.
It's really just take this as like the first step, just highlighting the main parameters. But then, we need to vary all of them.
And there's no spatial dependence on this fitting, right? You're just taking a single point spectrum?
Yeah,
Okay, cool. Thanks.
I think so, yeah.
Hey, JB, Lee Feinberg. So first of all, congratulations. I think this is one of the most significant, things that's gone on in the last year or two to enable HWO. This is not necessarily that we would only adopt this approach, but this as a tool in the toolbox to deal with some of our hard problems. This is really important work. So thank you for all you're doing there. And my question's a little similar to what you just heard, but with respect to Roman CGI, I mean, obviously it doesn't have the medium resolution spectrometer, but we will get a lot of information about the speckle noise, time varying, and I'm curious in your mind how much that will be directly relevant to HWO. I mean, at a minimum, it seems like we could do model validation that we could then apply to HWO. That's sort of, in my head, what might be the big value of it, but I'm curious what your thoughts are.
I've not thought too much yet about how Roman is going to help all that, but I'm guessing just determining the covariance matrix. Like, we need a model. Like, I think there's no conclusion yet here, but what it's highlighting is the importance of getting a good model of the noise, of the correlated noise, and maybe Roman is going to help with that. At least that's what I hope.
Okay, thanks.
Bruce, go ahead. Or do you have a microphone?
I was just going to plug again, which JB mentioned, Nicole Wolf's talk at in the coveted 5:15 Thursday slot. She's explored different correlation links in the low-res case and the impact of those on the ability to do the spectral resolution retrieval, and we have thoughts about how different optical effects can impact the correlation links. And it's definitely something we could try to learn from HCIT and Roman, although every optical system is different. So there's a nice trade of if the correlation length is 10 or 20 or 50 or 100. So stick around and listen to her talk, and the paper will go in soon.
Okay, I actually have a question. So, for R of 100, you have maybe a photon per hour per pixel. When you get to R of 10,000, that would be about a photon per week. Do you see any fundamental breakdown to going to these sort of deep Poisson levels?
We thought about this. I don't think we're in the Poisson regime for deep spectroscopic observations, like when we spend 100 hours on the planet. So this is actually like the flux budget and noise budget for the simulations. So yes, 100 photons per hour for the planet over the 20% bandpass. And then assuming we spend 400 hours on this, this is distributions of the number of photons over 400 hours, distribution over the 164 stars. And there's quite a few photons. And per bin, we're not in the photon noise. I mean, we have tens of photons per bin, even at slightly moderate spectral resolution. So that's Gaussian enough.
Okay, let's thank JP again. And our next speaker is Yifan Zhou from University of Virginia.
Hello, can you hear me? Good. All right. So I'm Yifan Zhou. I'm second year into my faculty job. And I'm pretty confident that in my career, we'll see a picture like this. But I'm not satisfied. I only see those dots turn into a picture like that. I only see exopixels turning into exo-worlds. But even if we have a 40-meter-sized HWO, Earth will still be 300 times smaller than diffraction limit at the 10 parsec away. So how do we achieve that? How do we achieve my dream to see the picture like this? Turn into the perspective from our solar system. Why do we want to point our space telescope at our solar system object? Because it helps to achieve my dreams. This is an example of Hubble and the Kepler light curves of Neptunes. Because the bright and the dark spots on Neptunes rotate in and out of our line of sight, it introduces modulations into its light curves. we use the same technique to look at brown dwarfs, very different object. The power spectrum of the light curves shows remarkable similarities. If we put on some reasonable prior constraint on the physical models for the brown dwarfs, using the power spectrum of these light curves, we can start to pull out the zonal and the storm structures on the surface of the brown dwarf. Earlier today, we heard the talk about hot Jupiters. For those tightly synchronized objects, we know it has this day-night contrast. And if we monitor it across their entire rotational phase, we can see that their maps can be explained very precisely by several low order of spherical harmonics. So the trick here is we can turn the time axis into the spatial axis and use very precise time-resolved observation to give us a spatial resolution that we can never achieve with diffraction limit. Why do we want to map the surface of the planet? Also, we learned earlier today from David's talk, right? The planets are not spherical calls. And we need to know the physical processes to drive those storms, drive the spatial features on the surface of the planet to accurately understand their atmospheric properties. Thanks to the very precise data coming from JWST, we start to use a variety of methods to figure out their spatial features. And they gave us this very important information about the diurnal cycles, weather patterns in these highly radiated, tightly locked planets. On the other side of this diagram, we also look at several highly objects that with very high internal heat, but not irradiated object. And their weather patterns looks very different. Within a day, storms can brewing, and their light curves patterns can totally change. And on this axis of irradiation heat versus internal heat, sitting in the middle is our solar system planets. Their radiation and the internal heat is about the same, and we haven't really been able to map planets like that outside of our solar system. And we need to start doing that. And how do we do that? We need to look at the direct image of the planets. To map the direct image of the planets, we need to achieve very precise light curves. We need a chronograph. We need a very, very stable telescope. And we learned yesterday the HWO will be excellent at doing that job. But we need to start to do our baby steps. Our baby steps, we can look at the most spectacular direct image of the planets, like the Beta Pig, like HRD 799, and use our best telescopes that are available to us, the James Webb Space Telescope, to see if we are starting to be able to achieve this requirement to map planets like that. So we picked the Beta Pig B as our first target to conduct this experiment. This is the brightest direct image of the planet so far. It's 3 magnitudes brighter than the next one. So if we can make this planet, if we can map this planet, the rest direct image of the planet sample is in the play. We know this planet is very dusty. We have identified silicate dust in its atmosphere. We also know that it's located in the highly dynamical debris disk that, in my experience, ongoing dust accretion to make its atmosphere even dustier. From ground-based high-resolution observation, we know this planet spins fast. And the fast-spinning planets, coupled with a dusty atmosphere, give us a signal to map the surface of this planet. We conducted our JWST observation to use 2-band to watch this planet simultaneously for 16 hours. And during these 16 hours, we're watching the deepest part of its atmosphere that is accessible to JWST to see if there is a dusty cloud changing in the atmosphere of this planet. Bracketed by the 16 hours of science observation, we also taking 2 sets of reference stars so that we can do our high contrast imaging stuff to pull out the signal from the planet to see what's the most precise light curve we can pull out for this planet. To get the light curve of the planet, it's a simple linear equation we need to solve. For each pixel, the light comes from the star multiplied by the fraction of the light comes from the star multiplied by a physical model for the star, plus the fraction of the light coming from the planet, multiply a model of the planet. And of course, there is some systematic term we have to deal with. Looking at the image, thanks to the powerful chronograph on JWST, we can use the reference star to do a very precise subtraction to review a clean image of this planet. Looks so lovely to me. And this is not just a lovely image. Because of this image, we can also solve two terms on this equation. The fraction of light coming from the star versus the fraction of light coming from the planet. What about the rest of the terms? What about the systematics? How bad is that? It's actually not that bad. To get an understanding of that, we pick a point to the opposite side of the planet, pull out the light curves, and see how it looks like. It looks flat, meaning that the level of systematics is actually pretty low. If we calculate the scatter in this light curve, it's on the pulsar noise level. Good news for me. And we can also do this exercise to many of the apertures surrounding the regions of the planet, as well as including the region of the planet. These are the serious light curves we got from this aperture photometry exercise. They all look kind of flat because we are not looking at the y-axis in the wide range. If we bring all the light curves together, one curve stands out, looks different from the rest. It is also the light curve coming from the aperture covers the location of the planet. I already see storms brewing, cloud forming on the surface of this planet. All right, of course, there are some systematics. If we look at the rest of the curve, there are some wiggles and bumps, and we can actually, using a principal component analysis to model it. Use just a few terms, no more than 3 terms, we can take it out in a pretty clean way. And the evidence of that is if we apply this principal component analysis correction to the data we have, even if the star already blocked by 90% of its light blocked by the chronograph, we can still pull out this tiny little bit of oscillation because of the stellar variability. Not just that, we also solved one more term. We know the intrinsic model of the star from this exercise. Now the only term left is the light curve of the planet. This is what we got so far. This is the 4 micron, a light curve of a beta peak B over 16 hours. It's not flat, meaning there are some surface features, perhaps rotate in and out of our line of sight. The light curve can be fit by the sinusoid. It's much better fit than the flat line. And if we trust this sinusoid, the period is introduced by the rotation of the planet. It has amplitude of about 1%, and the period is about 8.8 hours. I will explain what this period means. We also get simultaneously another color at 2 microns, shows almost the same patterns. And if we phase fold the light curves, it gave me some concerns. We have 2 segments of the data. It seems to show similar patterns. And these concerns alerts me to do additional work. We did a bunch of injection recovery tests, meaning to inject the planet with some known signals of variability. No matter what kind of signals we injected in, we can recover it. So give me an actual confidence that we are pulling out the right signal. If we believe this 8.8 hours is the rotation period of this planet, we combine with ground-based high resolution, project the velocity of this planet, we can constrain the spin axis orientation of the planet. It turned out it's aligned pretty well, being its rotation edge-on. And this planet also has an edge-on orbital axis, sits in the edge-on debris disk. It looks like all the axes seem to align, and it seems to make sense. And its edge-on viewing angle, if it's true, is also advantageous for searching for transiting moons. And given the precision we can get from these data, we can start to detect moons as small as Earth-sized. And tomorrow, I think there will be a talk from Marion Limbo focusing on the capability of detecting exomoons using HWO. To sum up with the observation part, we have collected really excellent data from James Webb that allow us to detect the photometric variability of this planet at a very precise, at a very high precision. This allows us to map the atmosphere of this planet, constrain its spin axis orientation, and perhaps give us the possibility to detect moons orbiting around this planet. Looking into the future, looking at this diagram, planet mass versus the forces driving the atmospheric dynamics of a planet. We covered the right part of this with JWST. I hope we can broadly survey direct image of the planets as far as we can with James Webb. I hope we can provide more contact with additional observations of brown dwarfs. And we need the chronograph, we need the stability HWO will give us. And I'm pretty confident that in 20 years, we'll be able to populate this map, this diagram, with maps of exoplanet. And by that day, I think my dream will come true. All right, thank you very much.
Okay, we have time for one question.
Yu Hu, JPL. Very nice talk. I wonder, do you try to compare the magnitude of the variation between the two color bands, or you break down your light curve into more wavelengths, and whether that could tell us the source of the origin of those variation?
Right. So far for this object, from the observational side, the best we can do is the variability of these two bands. They look similar. And I have done some preliminary comparisons of what kind of sources could introduce that. If you add a heterogeneous cloud, it could introduce similar variabilities in these two bands. But that's not exclude, for example, the possibility of a magnetic spot. It also introduced similar amplitude to these two bands. The best we can do so far is this photometric observations. If we can make like spectroscopic monitoring possible, using maybe JB can give us some ideas of how to do those observations, I think we'll have a much better idea of what the sources of variability.
Okay, let's thank Yifan again. And our last speaker for this session is Natalie Hinkel from LSU.
Great, thank you. Thank you all for having me. I'd actually like to start off by saying that I'm not here representing my own science. In fact, I'm here representing the Target Stars and Systems Working Group, which is a group that I led along with my co-lead Eric Mamajek. And so a lot of the information that I'm going to be providing to you today is actually from all these fantastic people here who did so much work over the last year and a half. So the Target Stars and Systems Working Group, or TSS, was tasked with a much different goal compared to most of the other working groups. So we weren't actually here to set up and think about really cool science cases. If anything, we were trying to get information from all of you, from all the different working groups, from all the scientists, even from the public, to try to really understand the different stars and properties that are important to measure from HWO. So I've broken down here our various objectives, but the real crux was that we wanted to identify and compile target informations, which includes stars, stellar and substellar companions, as well as circumstellar material that was vital or relevant to all science cases. So what we really did was we assembled and maintained a list of HWO stars and properties. This is something that we actually actively have going on now. And we provided analysis of which stars and stellar properties must be measured when. And so this really breaks down to precursor science, which is really the data that we need in order to inform the various architectures, which is a lot of what Lee talked about yesterday, but also the preparatory science, which is the data that we absolutely have to have before launch. So what we did, because this is a massive undertaking that we got input from all of you, is that we actually broke our group down into 6 different task groups in order to better understand all these different properties for the Exo-Earth related survey. So I'm going to go over them in no particular order. All right, first one is catalogs and databases. So this is really the group that set up and defined the target list. So we're now referring to this as TSS 25 with the idea that it might actually be updated in the future. This was built on direct imaging target lists that already exist, as well as an input catalog put together by Tuchow 2024 called HPIC. It also involved a lot of yield calculations. You can see the definition of the 3 tiers here, and it's also color-coded with the plot. And so first we started off with HPIC. HPIC has 13,000 stars. It's a lot of stars. So we started as the base. It's all the potential stars that could be observed by HWO. But everybody acknowledges it was way too much, so we really try to cut it down to tier 2. Tier 2 is where we started to take into account some of the potential system architectures, and so that's so it's sort of agnostic to them, at least as we know it right now. But also there were those stars that have a lot of potential properties, but maybe we're missing some key information. So there's room there. Then in tier 2 actually has about 500 total stars in it. Then tier 1 has 164 stars. This is based on the XEP list put together by Eric Mamajek and Carl Stapelfeld. This is basically the best of the best. It's the brightest. We have all the information for it. We know it as well as can be done. But with that being said, when people go forward or like, putting together proposals, we should not just be going for tier 1 targets. We absolutely need to do a combination of tier 1 and tier 2 stars, because at this point we don't know what we don't know, and it's vital that we have all of the information as possible before we get to HWO, and I'll be coming back to that in a little bit. All right, next group is fundamental properties. It was basically tasked with figuring out all the fundamental properties of stars. There's way too much to go into. This group did a huge amount of work, and you can see the breakdown here, where orange are the properties that weren't measured for the tier 1 stars and blue were measured. The crux of their takeaways is that we need increased precise ages for these stellar targets, very important for habitable worlds. We need better capabilities of dust detection. And then also we need a homogenization of high-resolution spectroscopy. So let's go into that a little bit more. So high-resolution spectroscopy gets us some really key information such as stellar abundances. So for example, yttrium and barium-2, really important for stellar ages. And then because stars and planets are made at the same time in the same material, we can use what's in the star for very key elements and actually make models of the planetary interiors. And this helps us a lot with defining various biosignatures. So for those elements, we're looking at magnesium, silicon, aluminum, titanium, and iron. Now, to date, we only have about 75% coverage of these specific elements. And if you're interested in these, we actually launched a new page as of Saturday on the Hypatia catalog, where you can go through and take a look at these target stars for tier 1 and tier 2 for all those stars that have abundances in them. So you can see this rough 75%. But they come from heterogeneous sources. They come from a variety of different places. So it's vital that we get these element abundances measured, which is also to say we need more than just bulk metallicity. We need more than just iron. That is not enough. We need these individual abundances. All right, activity and rotation. So this is really very fundamental properties that allow us to understand the planetary atmosphere and even make sure that the atmosphere is what we expect it to be. So this group put together information from 24 different published catalogs, and they did sort of a tiered hierarchy to sort of understand all of this information and pick out the best. So they figured out various completenesses. So for example, the highest completeness was for this average activity indicator, S index, for the S index and V sin I. Medium was for the average activity indicator, log RHK, as well as the rotational period. And the low was the periodicity of magnetic activity cycles and photometric jitter. Now, long activity monitoring absolutely needs to happen for a lot of these systems because some stars are currently quiescent, they're quiet, but they might be active later, and some stars are active now and they might be quiet later. So we need to have a sense of what their actual activity cycles are, so that way by the time that we go and observe them with HWO in the 2040s, we understand what we're looking at. We're not looking at something that's just flaring all the time. And I will note that in order to get the period of rotation, that requires a separate targeted survey because it has a different cadence compared to the magnetic activity cycles. All right, high energy emission. So this is really trying to understand X-ray and UV fluxes that are coming from the star, and this impacts time calculations, yields, as well as the understanding and interpretation of the spectra. So this group looked at sort of a breakdown of 4 different band passes. They looked at the X-ray, extreme UV, far UV, and near UV, and they looked at it specifically for tier 1. And so in this case, they were able to get at least 1 measurement for 92 out of 98 stars in these high activity band passes. They had got 20% that were well characterized in 2, and they got 2%, which is 2 stars, in all 4. And on top of that, this data was very heterogeneous. It came from a huge variety of sources. You can see it in this plot here, that there's a lot of it that's gray, which did not have observations, or they were failed observations. So the time is now to really get a lot more of this high activity data for priority stars, especially before key facilities retire. Multiplicity. All right, so this is really trying to understand the architecture of these stellar/planetary systems. So trying to understand, are there companions within the system? Are there, binarity, multiplicity, et cetera? So this group went and looked at the Washington Double Star Catalog. They looked at the Gaia survey. They also did a lot of individual literature sources to try to understand the multiplicity of these various target stars. In the plot that you're seeing the contamination estimate based on Gaia in 2040, so when we're expected to launch. And what you can see is that a lot of stars actually, have a star located within 10 arcseconds of them. That's very close. And especially when we want to direct image these targets, that's a lot closer than we'd be comfortable with. However, this isn't a well fleshed out survey because actually Gaia doesn't have 100% ability to resolve stars this far in. So it's absolutely vital that we go through and we look at different techniques. So we look at high resolution imaging, both optical and adaptive optics, interferometry, radial velocities, to survey as much about this as possible. This is not my field of expertise, but Zach Hartman is here. I saw him walk in, so please ask them. All right, finally, we have the extreme precision radial velocity. So in order to really get down to Earth-like sized planets, so small planets, small masses, we need to have sub-meter RV measurements. We're looking at 10 centimeters per second, not meters, centimeters. Right now, we're sort of able to get close to that with current instrumentation, but it's not actually fully there. And a lot of that is because there's issues with the models in intrinsic stellar RV scatter. So to date, there's about 47 of the tier 1 stars that have some kind of survey going on with EPRV facilities, but that's it. And this actually impacts a lot of the different precursor and preparatory science, as you can see. So we have the interpretation of the actual planetary spectra, the characterization of the long-term activity cycles, as well as the dynamic viability of these habitable zones. Because basically, if a star has a dynamically unstable habitable zone, then it is not an Earth-like host. So this is really crucial for us to understand. So to reach this 10 centimeters per second sensitivity, we need better stellar variability mitigation, and we also need coordinated efforts and analyses across the community, not just one-off and not just individual. So look, I know that this is a lot of information, and I threw out a lot of different properties that actually you all asked for. You said that these were the vital key properties that we need to measure, the key stars that we need to go after in order to have your science done. But the entire group and we recognize that this represents a huge effort on the part of the entire exoplanet community to get all of these observations. And especially for long baseline observations, there's a lot of them there. But when it comes down to it, we have to go after not just the best, we have to also go after ones that could potentially be targets for HWO, because we don't know what these stars might be doing later, and it would be truly terrible if we were to go and try to observe a star with HWO using this precious time that we've all already spent hundreds of hours on trying to understand, and then realize that it in no way could host a habitable star. So we must go after a larger than necessary sample to do these deep dive analyses for all of these properties. So by the time that we actually go and we observe, we understand and we know what we're looking for. And I think just having this extra data floating around for the potential targets that didn't end up getting observed, that's still helping us with our understanding of target stars and their systems. I think that's a fine consolation prize when it's all said and done. So thank you very much.
Okay, questions for Natalie?
Meredith McGregor, Johns Hopkins. So I was wondering if you could say more about the dust contamination data that you guys were working from. Is that only looking at hot dust like exozodi or cold dust or both? And where is that data coming from?
Do we have anybody here from that working group? Nope. Okay. My guess is that it was actually likely the cold dust that they were looking at predominantly. Again, this was done over a year and a half and is putting together information. So I don't know off the top of my head because, like I said, I'm representing 40 people. Yeah. But my guess was that it was the hot data, since exozodi is, I think, easier to look at than the cold.
Great talk. Of all the things that we need to observe, what do you think are the most urgent to get started? I'm thinking, you know, some facilities might be going away. Some of these things need long baseline. Where do you think are the most urgent things to be starting on?
Off the top of my head, I'm going to say the long baseline ones because we need to have started yesterday. With that in mind, we actually have a panel immediately after this with a lot of the people who put together this data, and we're going to ask them basically that question. So how about I not try to encapsulate it all and we wait like 5 minutes, if that's cool.
Okay, great.
Thank you.
Any other questions for Natalie? Okay, actually, Natalie is our moderator for this panel.
Ew.
So let's thank her again and ask our panelists to come up.
And if I could please invite the panel to come down. Also, one thing that I will mention is that a lot of the material that I presented here will actually be published in a variety of papers. So Noah Tuchow is putting together a paper for catalogs and databases. High Energy is led by Sarah Peacock. And then the Multiplicity group is, how do I play? Multiplicity has 2 papers. Oops. There we go. All right, so this is the Target Stars and ETA-EARTH panel. We brought everybody together here so that we could have a better understanding and sort of walk through the information that, that part of what I just talked about, but also open it up because, again, this is a lot of information that's put together by the community. So this is actually led off by this, this great figure put together by Vicki Meadows and Rory Barnes. And it's lovingly referred to as planets are hard. So in the center, you see basically the planet, and you can see the breakdown of the stellar effects, the planetary systems, as well as the planetary properties that go into what makes a planet habitable. At this point, we don't actually know which of these are the most vital, which would be great to have, or which are just sort of like on the side and Earth happens to have them because we only have one data point. But that's what a lot of this panel here is here to talk about, is to really have an understanding of like their point of view, their sense of things, especially as we try to figure out what are the most Earth-like planets, how common might they be, which is more of like the ETA-EARTH definition, and all the various things that we now need to go for in order to have habitable worlds be a successful mission. And so here are a lot of the properties that I just talked about, but I'm going to let the panel introduce themselves, give a brief overview so that you can understand where we're coming from, and then we'll switch to questions. Noah, why don't you start?
Okay. Can people hear me? Okay. So I'm Noah Tuchow. I'm a postdoc at NASA Goddard. I do work relating to target lists for HWO. So I recently, like around a year ago, I put together the HWO preliminary input catalog. And then more recently, I've been helping the Target Stars and Systems group put together the different tiers of HWO targets. So if you have any questions about that, come ask me, and hopefully we'll have a paper in the archive soon.
Hello. Okay. Hi, I am Tyler Richey-Yowell. I am a Percival Lowell postdoctoral fellow at Lowell Observatory. And I served on the TSS as one of the high energy emission task leads. And my research experience is in the UV and X-ray evolution of low-mass stars, particularly K-stars.
My name is Arvind Gupta. I'm a postdoctoral fellow at Noir Lab in Tucson, and I was a task lead for the activity and rotation group and for the extreme precision radial velocity group. My background is mainly in stellar characterization and planet characterization using extreme precision radial velocity measurements, so I think about both of those things together there.
My name's Rachel Fernandes, and I'm a postdoctoral fellow at Penn State. I'm also the co-chair for the Exoplanet Demographics Science Interest Group, or SIG2, so if you're interested in joining, please yell at me, not right now, but after the panel. My interests are broadly in exoplanet demographics and everything that comes with it, which is unfortunately stellar characterization, finding the planets, and then doing the demographics. But it's a learning experience, and it's been fun. And as a side gig, I also try to figure out ETA-EARTH, which I found out is important to this mission, so it's fun.
Good morning, I'm Renyu Hu from JPL. So my group work extensively on characterizing exoplanets using JWST and combined with planetary atmosphere models. For HAPWORTS, I was co-chair of the Characterizing Exoplanet sub-working group for START, and then the JPL Exoplanet Science Team lead for JPL for the project office. In this capacity, we simulate these planets. We perform mock retrievals to understand what's needed from the mission. And I do planets, I do not do stars, so I guess I'm here to provide perspective on how the stellar characterization could help and impact the planet characterization.
And unfortunately, Eric Mamajek couldn't be here. He was supposed to be the official moderator of this panel. I was supposed to be a panelist. However, he said that I could represent him in a way that I'm now infamous for doing. So if you can say it. Thank you. My name is Eric Mamajek. I am the Deputy Program Chief Scientist at the Exoplanet Exploration Office. I work under Carl Stapelfeld, which means that I'm Carl's junior. I know everything there is to know about spectral types, and with Carl, we put together the XEP list because we basically had the biggest spreadsheet you could ever imagine for about a decade. I'm very good at highlighting colors now. And we realized that it should be a paper. So I'm sorry that I could not be with you today. I say hi. And my name's Natalie Hinkel. I will be the moderator, unfortunately. I'm an assistant professor at Louisiana State University. I call myself a planetary astrophysicist because I work a lot with geologists and astrobiologists. I run the Stellar Abundance Database Hypatia catalog. So like I showed, we actually just launched the Tier 1 and Tier 2 stars, which we're really excited for. So I know basically everything about stellar abundances and how to go from stars to planets. All right, so without further ado, I will stop talking as much. I'm going to begin with a few questions to the panelists, and then at the end, we're going to pose some questions to the audience. All right, to the panelists, and actually, Renyu, I'm going to start with you first. We're going to go down the order. What is the most important data or information that we need to gather to inform science cases and simulations that will factor into the design of HWO when the mission concept review is in 2029?
Well, I can pretend that I'm a stellar expert, but I can just speak from, when I look at the science cases, especially the science cases submitted to the project office, and also my own research experience, some of the things that I, really come to mind. When I look at, your presentation, I realize that even for the, there's hundreds of potential target stars for the mission, the high energy UV spectral information of these stars are still quite incomplete, and that has to do with how we interpret potential planetary observations. For instance, that ozone was is considered one of the biosignatures which is produced from O2 through photochemistry, and that's one of the main reasons why we want to get to the UV wavelengths using a coronagraph or high contrast imaging. But if you want to do quantitative model between the amount of ozone to the amount of O2, the link there is photochemistry. It depends on how much radiation, UV radiation that the planet receives from the star. And it actually depends on the spectral shape of that UV radiation. So, and we know that different stars would have different output in the UV, even for the FGK stars. So I think it's important to build that understanding, ideally through observations prior to the mission. One other thing I noticed when reading the science cases, that many science cases seems to rely, or at least require, some understanding or constraints of the stellar age. And it's not just to understand like whether the star is young, like astronomers usually say, okay, if it's less than a few hundred million years, it's young, and all the rest is mature. But if we really thinking about habitable worlds and on Earth, for Earth, it takes like 2 billion years to reach the point that it can have the great oxidation events, and it takes billions of years to set up your biosphere if we just believe this one data point. So so the relevance here is not just the young and mature, so it's not that binary, but it's sort of, do we know a star whether it's like 1 or 3 or 5 or 10 billion years? And that kind of information would be greatly helpful.
Yeah, we definitely need more precise ages. All right, Rachel.
Right.
So I'll give my answer from an ETA-EARTH perspective, and I think ETA-EARTH has been defined several times yesterday, but not today. So ETA-EARTH is the something I had to do for my thesis. I'm doing it again. But yeah, it's essentially the frequency of Earth-like planets in the habitable zone of usually sun-like stars or FGK spectral type. So far, we have a grand total of 0 reliable planets that we can call like in that box. But we have a large abundance of short period planets that are about the same radii. And so we do what demographic people do best, which is extrapolate. And boy, do we really extrapolate, because if you look at the Kepler data set, which is one of the best data sets to do this with, the longest period planets get pretty sparse around the 80 to 100 day period. And 1 year, 365 days, is about 3 times as much area that we're extrapolating into. So my suggestion would be start looking at filling that gap. We might not get to the habitable zone, but we have areas in between. And I think TESS long period searches, Plato's long period searches are all well timed to be in that area. And that can help a little bit with extrapolation, that is controlling that other factors do not really impact it in any way, which is a delusion. But for now, we can work with it.
Oh, excellent point. Something I didn't even cover, so fantastic. Thank you. Arvind.
Yeah, so the composition of our target list is actually going to be one of the key science drivers for the telescope aperture, so for the size of the payload we need to deliver. Because the stars that we're observing, we need the telescope to actually be able to access all of their habitable zones. And like Natalie said, we really don't want to be spending valuable time on stars that in no way could possibly host an Earth-like planet. So one of the things we need to know ahead of finalizing the architecture is actually knowing which of these stars could host Earth-like planets. So from my perspective, from the RV perspective, is we need to know which stars have dynamically viable habitable zones. If a star has a giant planet, so anything between the massive Neptune and Jupiter, in or near its habitable zone, you will exclude an Earth-like planet. And for most of these targets, we don't actually know yet whether they have these giant planets in or near their habitable zones. So we need to do some short-term monitoring, starting probably now, to exclude the presence of those planets, or figure out whether all of our high priority stars have those planets, so we can move down the target list and figure out what size of telescope actually needs to be built.
Great idea. Thank you. Yep. Tyler.
All right, so from the high energy perspective, so besides what Renu has pointed out already, the stuff that we really need in order to refine the architecture right now is the near UV measurements, particularly down to about 200 nanometers. And so as we're doing yield calculations and trade studies and kind of determining what architecture we need, getting the exposure time from these near UV measurements is going to be quite important to see, like, okay, is this too much or is this too little? Like, what architecture do we need to achieve this science? You might have caught a quick glimpse of it in Natalie's presentation, because since she was covering so much. But we actually only have about 60% near UV either photometry or spectroscopy of the tier 1 target stars. Only about 60% of those have those measurements. But most of those don't actually go down to 200 nanometers, which is where the chromosphere really starts to become an issue for, particularly for the G and K stars. And so we're really missing out on the chromospheric activity of these stars, even with the measurements. So it's only about 8% of our target stars actually have reliable chromospheric measurements that will be needed to inform the architecture. And models currently don't really include this very well. And so we have an estimate, but we've seen so much variation from star to star, even with the same age and the same spectral type, that getting actual measurements of each of these priority stars is going to be very important.
Thank you. Yeah, perfect. Noah.
So I'd like to echo what everyone else has previously said because I'm the last of the panel. But so high precision OV measurements in order to not only characterize planets in the habitable zone, like potential Jupiter planets in the habitable zone that might make it dynamically unstable, but also the presence of unseen binaries because unseen binaries might be a major obstacle to finding an Earth-like planet in the habitable zone, or even like being able to host an Earth-sized planet in the habitable zone. And also along with that, like circumstellar material, so exozodi will play a large role in determining which stars actually could host detectable exo-Earths around, but we don't know the exozodi for most of these stars that we're actually interested in looking at. From a yield modeling perspective, I'd like to echo what Tyler was saying about UV fluxes. We'd like to image these planets in the UV, but we don't necessarily know how many of these planets are actually going to be visible in the UV, and just we want to be able to do yield studies in order to determine the yield of planets in the UV, but we need actual UV measurements for that. We currently have model estimates of what the UV might be for these stars in the input catalog, but ideally we'd like a larger UV survey of near UV fluxes for these planets in order to determine like the approximate yield of planets, which we can actually determine the ozone concentrations.
Yeah, totally fair. All right, thank you all for that. It was great. In additional information, what I tried to provide too quickly, and then also some supplements for ETA-EARTH. So Rachel, actually, what are the uncertainties in ETA-EARTH or the frequency of Earth-like planets? Like, how can HWO help our understanding?
I think if I could provide the uncertainties on ETA-EARTH, I'd be solving a really big problem right now without any math. So with that, I would agree that the uncertainties based on everybody who has done this calculation is roughly between 10 and 50% right now, and I would agree with that. People have been considering, people actually have been working actively on redoing the entire Kepler analysis with better statistical tools to see what's going on there. That's been done, I think, at NASA Ames, if I'm not wrong. People have also been looking at co-occurrences. How do giant planets existing in the same phase space affect Earth-like planets and a bunch of other stuff like that? But yeah, ETA-EARTH is uncertain, but I think when thinking of ETA-EARTH, you also have to think about beyond this mission, because this is the next mission, but not the last mission NASA is going to put forward, hopefully. But I think ETA-EARTH is important for this mission, but HWO itself is going to measure ETA-EARTH. It's probably the best designed mission to measure ETA-EARTH. So regardless of what we do before, I think it's going to get us one step closer to actually very well like understanding what's going on in that habitable zone. And when you synthesize that with what we know of far off planets and what we know about close-in planets, you can finally start putting like Earth and solar system into context.
Excellent point. Yeah, no, I really appreciate that. All right. Renu, actually, quickly, what do you think we need to know about these targets and systems now during mission design? And what do you think we'll need to know by the time HWO launches? Short.
I guess a lot of things. And I just want to echo other panelists and particularly point out that I think a big way to know whether extreme precision radial velocity astrometry can detect some of those Earth-sized planets in the habitable zone of those target stars, and if there is a path in the next 20 years to do long-term monitoring and understand the stars' variabilities and all the noises from the astrophysics well enough so that we can at least have some the targets in hands before launching the mission.
All right, fair. All right, now to open it up. So to the audience, I'd like to ask, what additional information do you think is needed in order to support HWO design, the science cases, and the yield simulations? And what urgency would you assign these? Do we have any people willing to stand up and be the first? Anybody? JT.
With photochemistry being responsive to changes in the star light, you can look up and see the Earth's atmosphere changes on a daily basis. How much information do we need to know about the UV flux of the star that's exactly contemporaneous with the real spectra we're taking for biosignatures? Do we need to be able to observe in the star in the UV right then, or can it be right before that observation or right after that observation? Because that might impose constraints on our instruments or the operation of the instruments.
Yeah, that's a great point, and I didn't even I sort of glossed over contemporaneous science, so that's the science that's taking place at the same time or nearly the same time as HWO observations, so excellent point. Others?
I don't know the answer to my own question, so
No, yeah.
Somebody there has.
Anybody on the panel? Okay.
I don't really know.
Sorry. So I think that especially there's been a few studies on M dwarfs showing that the reactions from UV flares can impact the photochemistry very rapidly, and that it can also both go away in a couple of, I believe it was days as well. And so I think having that contemporaneous UV would highly elevate the science return of these observations.
All right, any comments from the audience about what you think is important? Like this group? Oh, Evgenia. Okay.
Thank you. Evgenia Shkolnik, ASU. So just to follow up on that answer, one thing we have to do is model whether that impact, yes, there's an impact, but is that impact going to be measurable with HWO before we dive into needing simultaneous observations?
Anything else from you all as scientists? Yeah, online.
Okay. So Courtney's Dressing's online, and she asks, I think specifically for Rachel in terms of how and the importance of things we need to measure. Can you comment can you comment a bit on the need to measure densities of cooler planets, because what we get with transits is just the size, and how results from the various detection methods, RVs, astrometry, transit, microlensing for M dwarfs, could be combined to better estimate ETA temperate planets as compared to ETA Earth-sized planets?
Yeah, good question.
I'm assuming she means temperate small planets and not temperate big planets?
Yes.
Oh, okay.
There's a lot of words. I was trying to get it in.
Okay. I think density would be useful. I'm actually a break proponent of actually starting to do demographics in density space, because I think we did the best we can, and I think radius is fantastic, and I think mass is fantastic. You know, what's better when we put that together, and we're like, now we start doing in density space, because I think that might shed light on something like the radius valley, for example, because it shows up in radius space. Does it show up in density space? And can that be something that we could use as maybe a pointer or something we have in a peripheral vision while figuring out habitability of Earth when it comes to density? I don't do radial velocity and masses and density, but I could, yeah. But I think it's a good idea to start doing that, and I'm a big proponent of it.
I think that if we want densities, we first need to do the precursor observations necessary to get planetary masses. So I think that requires like OV surveys and also advances in astrometry. So we need to be kind of planning on those ahead now, so that once we have observations with HWO, we'll be able to look back at like a baseline of OV observations or astrometry observations.
I totally agree. And actually putting on my own scientist hat. So to date, only 20% of planet hosting planets in the NASA Exoplanet archive have mass and radius. And of those, only 11% are small planets. So that means that we actually don't know very much about the mass and radius of small planets. And you absolutely need to have mass and radius in order to characterize a planet and say whether it's Earth-like, is it super Mercury, is it like a mini Neptune. So I think it's absolutely fundamental that we get these properties now, starting these longer baseline measurements now, because there's no way that we're gonna really have a true understanding if a planet, is Earth-like, if it's rocky, if there's, mantle, crust, that sort of thing, or if maybe it's like a Mercury that's mostly made out of a core. And if that's the case, then that has a totally different definition of habitability, and it's actually a lot harder for a planet to be habitable. So I think in a lot of this, we need to do as much as possible to characterize the planet itself, its interior structure, because when we're going and detecting biosignatures, we have to be able to separate that from any signatures that we're getting from the planet. So that means outgassing, volcanoes, things like that. So there's no way that we can say definitively that there are biosignatures without saying it's definitively not coming from the planet. So I think, that's a great question, because it's really important that we understand these planets as they are as well as possible. And that's, I think, the true way to actually get to potential biosignatures.
Yeah. So just to add to that, Natalie made the good point that we definitely do need these densities, we need the masses. And sure, we could wait until we've actually done the HWO survey to do that, but these things take a decade plus. So we don't want to measure all the atmospheres and then have to wait another decade to actually be able to interpret the results. So it's important to get this stuff started now in the decades leading up to the launch.
Excellent, perfect point. Up at the top.
Yeah, just a short remind for a subsample of the sky, about twice 2,200 square degrees, what you are asking will probably be very likely provided by Plato, because it's already in the purpose of the Plato to search for, down to Earth analogous, but anyway, Earth-like planets in habitable zone. And within the mission, there is also the full radial velocity follow-up. It's a part of the mission for the mass determination, so the density. So I would say, particularly for small planets in 10 years or so, there will be this information, at least for a subsample of the sky. And there is a poster tomorrow. We have already checked that there is an overlap between the targets of Plato and the preliminary HWO targets that have been published. So, and also the astroseismology for ages and high precision masses and radii of the stars will be available from the same kind of data set.
Excellent
So,
point.
as I say, it's one tenth of the sky, but at least for that, there will be some
No, this is great, because I didn't actually think Plato had released the target list yet, because I'm part of the working groups on that as well.
Yep.
And so it's great to hear that you have a poster. Definitely, that's important information. All right.
Yeah, you'll find it tomorrow.
Thank you. One last question at the top, or comment.
Vincent Fernandes, UCL. Sorry, I was going to make a similar comment about Plato, but just to say that to add to it beyond Plato giving light curves, and I think a pretty good constraint on ETA-EARTH and lots of products on the stars, perhaps contrary to popular belief, a lot of the Plato data will be public. The vast majority of Plato data will be completely public. So if anyone wants to chat about Plato, there's several members of the Plato science team in this audience, including myself, so feel free to have a chat. But I think it will deliver a lot of things pre-HWO in the next few years.
Great, thank you. All right, there's a lot of information that we covered here, but it's clear that our work is cut out for us. I mean, a lot of people are like, oh, why are you starting out so far in advance? And I think we made that very clear why. There's a lot of really key information that we absolutely need to measure now in order to have HWO be as successful as possible. So let's thank the panelists again.
Thank you, everyone. Next, we're going to a poster session. The poster chairs are Raisa Estrella and Rob Zellum. I don't know if you're in the room, if you have any announcements. Okay, and we'll reconvene at 10:55, but JNS does have one announcement.
I know I'm keeping you from your coffee, and this announcement will be even worse because I'm going to keep you from your lunch. So somebody kindly pointed out that we don't have a conference photo in the schedule. we will try to cram everybody in here right before lunch. So don't leave after the end of the next session. We're also going to bring the people from the overflow cabin into this room. So that's the announcement. But let's give a really big round of applause to this morning's speakers and to our poster co-chairs who have done an enormous amount of work wrangling these 100 posters.